Hello everyone.
Hello everyone.
Just have a wait, guys. We will be starting the session in a few minutes. Okay, guys, don't forget to share the links with your batchmates and friends. Must be sure that you like the video and subscribe our handle. We will be starting the session within few minutes.
Keep on sharing the link with your batchmates.
So, greetings to everyone. I, Deepak Kumar, pursuing my BTech from the Information Technology Department of Batch 2K21.
I, Ayushi Tiwari, pursuing my BTech from Production and Industrial Engineering Department of Batch 2K21. Welcome you all on behalf of IETE Students Forum.
It is with immense pleasure we notify you that we have our respected director, BIT Sindri, Dr. D.K. Singh sir, with us on stream. We invite him to give a few words of encouragement.
Very good afternoon. Namaskar. And on behalf of IIT BIT Sindri chapter and Department of Electronics Communication, I welcome first the expert, Mr. Akash Vaibhav. Akash is here. He is connected.
Yes, sir. I am here.
Yes, sir.
Very good evening, sir.
Very good evening. This is a great pleasure to an institution when the graduate of this department comes as an expert. So salute to you.
Thanks a lot, sir, for the
And
appreciative
once
word.
again, welcome all the IIT member, the faculty member, and the other students who are connected to this program, because the topic chosen by the IIT is a very important and very challenging topic, VLSI challenges and the opportunity. India has witnessed the development of IT and IT-enabled services, but I am very thankful to the government of India that they have taken the initiative to make India as a manufacturing hub. And in this manufacturing hub, the semiconductor is going to take initiative, right? Take the lead. So recently, Apple plants and the other semiconductor manufacturing plant in the Gujarat is going to be installed, right? Vedanta and the other company, they are going to set up. Uh, so the VLSI challenges and the opportunity, you see the world, this is the technology which has penetrated to the masses. I was listening to the Bill Gates. Bill Gates once was mentioning that automobile industry is 200 years old, but still the common man cannot afford it. Why it cannot afford it? Because a lot of technological development, a lot of research has not taken place. But you see the ICT, electronics and communication industry, how much R&D has taken, how much the best mind has provided the input, how much the the world engineers, all the engineers of the world has done their contribution so that the chip has become very less costly, and it is affordable by the common man. So the India is going to witness this technology, and unless and until we are not exporting in the area of the manufacturing, we cannot say that we are the best in the economy. So right now we are the fifth, and I hope with semiconductor manufacturing, uh, the defense manufacturing, and the other manufacturing initiative, we will be the third best economy of the world. So Akash is now the expert of these areas. So it will be a great opportunity to me to listen, Akash, what are the recent development that is taking place in the area of the semiconductor. And I hope the Department of Electronics Communication, the HOD, Professor Imtiaz Ahmed, and the other faculty member will take the initiative as per the advice given by our expert, uh, uh, Mr. Akash Vaibhav. So with these words, I'm handing over to the organizer for continuation of this program. And I wish all the best for this workshop. Thank you very much.
Thank you, sir, for your wise words. I am sure the students learned quite a lot. Thanks a lot, sir.
Let me give you all a brief about what exactly our club does. IETE Students Forum is a techno management club of BIT Sindri. It is a sub branch of the IETE national body which aims to empower youth through technical education and skill development. Here we conduct webinars and workshops on various technical topics.
Today, we will be overseeing some important topics and techniques on VLSI. He will also be sharing the experience with us. Our major discussions will include the challenges and opportunities involved in the VLSI deep sub-micron realm.
At the end of the session, we will be conducting an exciting quiz competition and then we have something for winners as well. So stay till the end and don't miss to fill out a feedback form as we will be providing certificates to the candidates.
Before starting the session, let's hear out to our today's speaker, Mr. Akash Vaibhav. He pursued Electronics and Communication Engineering from BIT Sindri. He is of 2K13 batch. He did his MTech in VLSI and Embedded Systems from IIT Patna. Currently, he is a Senior Design Engineer at ST Microelectronics. Have a big round of applause.
All the participants are wholeheartedly welcome to our program. We hope you all enjoy the session. So without further delay, let's commence the webinar with enthusiasm and positive vibes. Welcome you, sir. We are handing over the platform to you, sir.
Okay. Very good evening to all the students, to Director Sir, and to the hosting members of IETE Students Forum, and to their professor in charge, Dr. Imtiaz Ahmed Sir. And first of all, I'd thank you all for extending this opportunity to give back something to the alma mater. I was there in the institution back in 2019, where I had few words about the opportunities in the VLSI industry. And back then, when I met Dr. DK Singh sir, our director, he was very keen on having more sessions, but due to the pandemics, we could not continue it. And I'm really happy that now we have moved over to online sessions, which are much easier to conduct. Speaking from the expert point of view, because like I was able to do my office work, and in the evening I was ready to give this session. So thanks a lot to the technology and the people who are using it so wisely. Okay, so I think sufficient has been said to introduce. So I'm Akash. I have not been knighted yet by the Queen, so I'm just Akash, not Akash sure yet. But I will be very happy if someone recommends for the knightation. Then I will be Akash sir. So please feel free to call me Akash, not Akash sir. Okay. So VLSI, if we can have your comments, when you hear the word VLSI, what comes into your mind? Just type away in the comments so that we can have a little appetizer before delving into the main technical terms. What do you understand by VLSI? Anyone? Okay. Okay. So I think I don't know how this the chat works. So let's start. Uh, am I audible? Team, is my screen visible and am I audible?
Yes, sir, you are audible, sir.
Uh,
Yes, sir, you are audible.
can you people hear me?
Yes, sir.
Okay. 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 So my screen is visible as well, right?
Right, sir.
Okay. Perfect. Shall we start then?
Yes, sir. We can continue.
Okay. Thank you. So when we started having this discussion on what exactly should we do the webinar on, like we had a lot of areas in which we could talk about, but the students were very keen on understanding or having a glimpse into the semiconductor world. And when we say semiconductor, VLSI is just like the second name to it. So let's start with the introduction. So basically, I have structured this talk into three sections. First, we'll be having a brief introduction of what is electronics, what is VLSI, and what are semiconductors. I have been told that a lot of the audience are from first year, and so the first two sections are meant for students who just have the basic understanding of electronics. If you know what is an electron, what is an energy band gap, if you know the periodic table, which we all would have learned during class 12th, so this webinar would be very helpful to you. Don't panic if things get too heavy, because of course this is something which is uh, of the master's level, but we have tried our best to mellow it down for the bachelors. So please feel free to ask as many questions as you have. I personally would have preferred that I be interrupted between my presentations, but because of this online mode of delivery, I think we should keep the questions to the end of the session. Please quote the slide number where you have the suggestions or questions so that we can quickly go back to understanding your questions better. Okay, so now let's start the actual session. So first, what do we exactly mean by electronics? Like we have electrical engineering and we have electronics engineering, right? So when we say electronics, it simply pastes an image of per se a gadget or per se transistor or resistor. So if we go to the etymology of the word electronics, it consists of two words. One is the electron, the other is X. Electron is the electron, and X is pertaining to anything that it is added to. For example, if you say mechanics, then something which is meant by the physical movement of anything is called mechanics. Similarly, electronics engineering, to be precise, is the field of engineering which deals with the study and manipulation. Here, the two words, study and manipulation of electron flow. So in the entire in electronics engineering, we just do two things: the study of the electron flow and the manipulation of electron flow. All the devices that we have in electronics, per se a resistor, a transistor, a diode, MOSFET, IGBT, all these devices are simply meant to manipulate the electron flow. All the electronic devices that we see, for example, if you see an example of an LED is nothing but an light emitting diode, right? So in that also, the energy of the electrons, when they move from the conduction to the valence band, that energy is dissipated as visible light. So even the light that we are getting out of LED, it is just coming out as a result of the electron flow. So that is the basic meaning of electronics. Then I have added this just as an appetizer of course, we will be dealing with VLSI in much deeper terms as we move further in the presentation. So VLSI basically stands for very large scale integration. So if you go through the abbreviation word by word, then very large is synonymous to massive, and integration is the integration of multiple components onto a single silicon wafer. See, circuits can be of two types, right? For example, if we have a PCB, the printed circuit boards, there we have individual resistors, we have individual capacitors, and we can have individual inductors, and they are connected per se in some fashion, right? Most probably through soldering on a printed circuit board. So all these individual components that you see, and an integrated circuit, per se a transistor, a capacitor, or even a diode, these all have to be manually or automatically be connected through a physical metal pin. That is, when they were manufactured as a discrete component. So each resistor was manufactured separately, each capacitor was manufactured separately, and each inductor was manufactured separately. But when we come to the integrated circuit, the word integrated circuit means that everything that circuit needs, maybe a resistor, an inductor, or a transistor, that is fabricated directly onto the silicon, precisely onto a silicon wafer. So VLSI is the field of engineering which transforms the circuits which are designed through EDAs, that is electronic design automation tools, and the entire circuit is fabricated on a silicon wafer. Of course, we'll be going through the details of the fabrication process, the design of the electronic circuits in detail in this presentation. So just for an overview, VLSI is just a method of designing the circuits to be printed onto on a silicon wafer, and the entire circuit in itself is printed on the silicon, not discrete components. For example, if you might have got a chance to see the processor of your computer, per se an Intel i3, or if you are lucky, the processor of your mobile phone, say Snapdragon 888. So you see that the processor in itself is just one single entity. You cannot see the components inside that transistor, that IC, that integrated circuit. It is packaged as a black box to you. But that single piece of IC may be incorporating billions and trillions of components in itself, but they are all manufactured together on a single piece of silicon wafer. So that is VLSI for you. Okay, so before delving into VLSI, I want to spend some time on what are semiconductors and how do we control the flow of electrons in semiconductors. So electrically, if we see, anything on the face of Earth can be divided into three sections electrically. The first is the insulators. Insulators are, for example, they are like plastic. These are the materials which are very poor conductors of electricity. Then there are the conductors, the metals, which are excellent conductors of electricity. So if we see from the physics point of view, then we have two energy bands for any material. The one is called conduction band, second is called the valence band. So every material has electrons in it. We know that from the atomic theory, but not every electron can participate in electric flow, right? Even plastic has electrons in it, but it cannot conduct electricity. The reason being that an electron can only participate in electricity flow if it is residing in the conduction band. If it is residing in the valence band, then it cannot participate in the flow of electricity. So in the case of insulators, the energy difference between the valence band and the conduction band is more. So the electrons present in the valence band cannot jump into the conduction band, and consequently they cannot conduct electricity. If we see conductors, on the other hand, we see that the conduction band and the valence band overlap. So all the electrons in the valence band are free to constitute to the electron flow, that is electricity. But there are materials which are unique. So semiconductors, as the name signifies, they are semiconductors, partial conductors. So in the case of semiconductors, the band gap is small. For example, if I take the case of silicon, then band gap is of 0.7 electron volt. So if you provide if the electrons of the valence band are excited, and if they accumulate energies equal to 0.7 electron volt, then they can jump to the conduction band, and hence they can constitute electricity. So due to this unique property, semiconductors are an ideal material for manipulating the flow of electrons. As we discussed in the definition of electronics, that electronics is nothing but the engineering of study and manipulation of electron flow. And if I have a material whose conduction property itself can be modulated based on the energy that I am giving to that material, then it gives me an immense power to control the electricity that can flow through that material. So VLSI is running entirely on semiconductors. Now, what are these semiconductor materials? So in the periodic table, the fourth group materials, wherein the materials who have 4 electrons in their valence band are semiconductors. The popular semiconductors are silicon and germanium, and these are the atomic diagrams for silicon and germanium itself. So here it is worth noticing that in the valence band, we have 4 electrons each for silicon and 4 electrons each for germanium. Now, when we have a pure silicon lattice, so each of the 4 electrons form a covalent bond with the other silicon atoms. For example, if we consider this silicon and this silicon, so this silicon has these 4 electrons in its valence band. Consequently, these neighboring 4 silicon atoms also have one electron corresponding to this particular silicon in between. So they form a covalent bond between them. Now, as we know that covalent bond is a very strong bond. So if 2 electrons are bonded by covalent bond, then they are not free to roam about in the lattice. That means these electrons cannot constitute to electricity, right? But if they are excited per se thermally, so that these electrons can jump out of this bond, so that they become a free entity, and if an electric field is applied, then these are free to move in the opposite direction of the field, or in the rising potential of the field, right? So this method of conduction is prominent in the intrinsic semiconductor. What does intrinsic mean? Intrinsic means that it is pure. So when I say pure, that means the entire lattice is made entirely of silicon or germanium materials, right? But for intrinsic semiconductors, the conduction is very small, because breaking a covalent bond in itself requires a lot of energy. So what we do in semiconductors, we do a process called doping. We would have studied it in the class 12th, that doping is the process of introducing fifth group or third group materials into the fourth group material. So fourth group material, for example, silicon has 4 electrons in its valence band. However, a fifth group material will have 5 electrons in its valence band. Consequently, a third group material will have 3 electrons in its valence band. So when the lattice is introduced or per se doped with an impurity, what is an impurity? An impurity is a fifth group material or a third group material. Then the number of electrons which are needed for forming covalent bonds with the silicon atoms around the impurity varies. For example, if we go for doping with fifth group material, per se phosphorus, then now we know that phosphorus has 5 electrons in its valence band. So even after forming covalent bonds with 4 corresponding silicon atoms, it will be left with 1 electron which is free to move under the influence of an electric field. Consequently, if we choose to dope the pure silicon lattice with a third group material, per se indium, then it only has 3 electrons. So it cannot form a covalent bond with the fourth neighboring silicon atom. So there is a vacancy present in this. So electrons of a corresponding silicon can move to this covalent bond and vacate its original place. So it would seem as if this vacancy, which is called a hole, has moved from this point to this point, per se point 1 to point 2. So, and when will this electron move? When there is an electric field opposite to the direction of the movement of electrons. To make the understanding better, if we consider this hole to be a positively charged entity, then we can say that a positively charged entity hole can move in the direction of the applied electric field, right? Physically, a hole does not exist. It is just a vacancy or the absence of electron. Just like darkness is nothing but the absence of light, right? So hole is nothing but the absence of an electron. But since an electron can jump from point 2 to point 1, thereby creating a vacancy at point 2, it would seem that the hole or the vacancy has moved from point 1 to point 2. So when the conduction is by electrons which have a negative charge on them, we call the corresponding doped semiconductor as n-type. And if the conduction is due to holes, the doped semiconductor is called p-type. Next, I only need to introduce one device, which is the MOSFET. So as we know that electronics is nothing but the engineering of controlling the flow of electrons, right? So for that, we have different devices. We have a very simple device, diode. So if it is a diode, then if it is biased, that is, if a potential is provided to it in this manner, I mean, the positive is here and the negative is here, then it can pass the current through it. And if this biasing is not there, or even if there is an opposite bias, the diode will not allow this current to flow. So by choosing the biasing of this particular diode, I am able to control if electrons can flow between point A and point B. So this is an electronic device, a diode, right? But in the field of VLSI, the device in our interest is called MOSFET. MOSFET is an acronym for metal oxide semiconductor field effect transistor. I'll explain it word by word. So this metal oxide semiconductor has something to do with the architecture of this device, which we will be discussing soon. The other thing, field effect transistor, it is denoting the method by which we control the flow of electrons. For example, in the case of diode, we can choose whether electrons will flow through the diode or not by applying a potential. A potential is nothing but a voltage gradient. Gradient is field, right? So diode is also field effect device. Now, transistor, we know that it is of two types, a current control transistor and a field effect transistor. Current controlled transistor is a BJT, bipolar junction transistor, and FET is field effect transistor. So a field effect transistor, or precisely a MOSFET in our case, works in this manner that if we have a potential applied between the source and the drain. So basically a MOSFET is a transistor or a device having four terminals. One is the source, second is the drain, third is the gate, and fourth is the body. So usually for simplicity, the body and the source are shorted. For example, if you see in the schematic, the body is this fourth terminal. It is shorted with the source terminal. So effectively it becomes a three-terminal device. So we'll be discussing the working based on just simple three terminal device. For example, the diode was able to control the flow of current. Consequently, the transistor is also able to control the flow of electrons, but it is also capable of amplifying the current that can flow. So if we go into the working of this MOSFET, then it works like this. If a potential is applied between the source and the drain terminal, then we have a field between this channel region. But for an electron to flow, there should be a continuous path between it. For example, if you have a metal and another metal, but if you have a air between them, then current cannot flow, right? Because electron needs a continuous path for flowing. Similarly, in this case, this region is N plus type, that is N type. So the carriers are electrons here. This region is also N type. So the carriers are electrons here. But the substrate is of P type. So this region has very few electrons in it. Because the region has very few electrons, so even if the field is present in the channel region, current cannot flow between the source to drain. But if I apply a positive potential on my gate, which is the controlling terminal, then it can attract electrons present in the body so that we have a very thin layer of conducting channel in it. And once that conducting channel is established, then because of the potential applied between the source and drain, electrons can flow between the source and drain. Consequently, we will have a current flowing in the circuit. Now, how is this device constructed on a silicon wafer? That has to do with the architecture and its nomenclature. See, the first name is metal. Metal is used for the connections. So the terminal, source, gate, drain, and body, these all are made of metals. Then there is an insulator between the metal and the substrate. Substrate is the silicon or germanium, per se, a semiconductor. Why is there a oxide or an insulator between it, so that there is no electron flow between the gate terminals. So the controlling circuit will not have any current flowing through it, but the control circuit, which is between the source and drain, it will have the electrons flowing through it. So there will be no current flow through gate, but there will be current flowing through this, through the drain, between the drain and the source. So how this is fabricated on a silicon is like this, that we have a plain silicon wafer. We dope an area by heavily bombarding it, or by heavily doping it with fifth group material, so that it is n type, another area as n type, and we fix metal terminals on it, and then if we apply potential between them, then we can control the flow of electrons. So this is the basic transistor which constitutes to my VLSI, right? So without going much deeper into the physics, I would like to move to the VLSI part, which is just an abstract, an overview, and it will give you a horizon of what you can learn during your BTech days and what is actually being done in the industry, right? If you have understood the physics up till now, then the way ahead will not be very difficult. Even if you have not, then it is always better to build the foundation even after the building is built, right? So let's take an example of a car. So why I have taken the example of a car? Because if I would have chosen per se a laptop or a mobile phone, then we all know that it is having a lot of semiconductor or say integrated circuits in it, and the majority cost of a laptop or a mobile is based on the cost of electronics that goes into that particular device, right? But even if we don't see electronics in a car, you would be astonished to know that if you buy a high-end car, then maybe you are paying up to 60% of your cost because of the electronics that the car has. A very easy and recent example that we have, when the pandemic hit, so the fabrication of electronic circuits stopped, or per se stalled. Not entirely stopped, but the efficiency was reduced. And there was a shortage of semiconductor chips. And because of that shortage, car manufacturers were not able to make their vehicles. Car is a mechanical thing, right? But at the heart of that mechanical machine is electronics. And even if the machine is completely built, if you don't have the electronics for it, you cannot sell the car. So the slowdown in the manufacturing of cars, or per se in entire automotive industry during the lockdown, was majoritarily due to the shortage of semiconductor chips. Where are these chips available? Right from the engine to anything between your camera to the dashboard to the sunroof, or the safety features like airbag, or ABS, EBD, everything is controlled by electronics, or per se a VLSI chip sitting inside your car. So for example, if we take the example of a power train, so the amount of fuel that your engine will consume, that is also controlled by the chip which is sitting inside the motor. Infotainment, of course, is very visible. The audio connectivity and all, it is very visible. Now we have the concept of connected cars. So for example, in Hyundai, if you have the feature called Blue Link, then you can track the car just by using your mobile phone. So your car is connected to internet as well. Then we have the steering systems, the braking, all are controlled by electronic systems and electronic chips sitting inside the car. So you see, the electronic market is much more than it is visible to us. Even if we see it every day, we might not be aware that the feature that we are using is actually a gift of the electronic industry, right? So now if we talk about the challenges that we engineers try to solve in VLSI, they can be summed up into two different aspects. So the first aspect is trying to fit in as much logic into as small place as possible. So in this, we have something called the Moore's law. So it is not an actual law like Newton's law or any other law, which are actual laws which exist in the physical world. Moore's law is more of an observation which Gordon Moore had. So Gordon Moore was the co-founder of Intel, and during the early days of integrated circuits, he saw that the number of transistors per square micrometer doubled every year. So if I have a 1 millimeter square silicon area in 1970, and if I was able to insert say 50 transistors in it, then when 1971 will come, I will be able to accumulate 100 semiconductor transistors in the same 1 mm square area. So he proposed that the pace of the advancement of semiconductor industry should be such that we are able to double the number of transistors in the same silicon area every 1 year. But this timeline of 12 months was later calculated precisely to be 18 months. So now, up till around 2002, 2005, this pace was rapid. So previously, we had the size of the transistor. Basically, the number of transistors that you can fit inside a 1 mm square chip will depend directly on the dimension of individual transistor, right? So right now we are sitting at something around of 2 nanometer, 2 nm. So the entire structure that we saw up till here, the entire structure is just sitting inside 2 into 10 to the power of 9 meters. So you see, precisely the channel length is the technology length. What is the technology length? The uh, dimension of individual transistor in that technology. So like back in 2012 also, we had the technology at 180 nanometer. 180 nanometer. But you see, just in a matter of say 7-8 years, we have moved the technology to 2 nanometer. 5 nanometer, 3 nanometers are the norm today. But the word is that we will be jumping to 2 nanometers soon. So you see, in the area where I was able to insert one transistor, now I'll be able to fit in 180 transistors. So this pace is now starting to slow down because technology has its limit. Jumping from 80 nanometer to 90 nanometer to 45 nanometer to 28 nanometer to 14 nanometer to 8 nanometer to 5 nanometer was easy. But now we are reaching the dimensions of an individual atom. So we cannot go to very quantum depths, right? So the structure in itself has to change. So how do we design the physics of a particular transistor so that we can get the performance to double per square micrometer is the latest Moore's law. So what does that mean? If I have a 1 micrometer by 1 micrometer chip and it was able to do certain X amount of computation in say 2022, then after 18 months, this particular X computation should be doubled. So this 1 micrometer cross my 1 micrometer chip should be able to perform 2X computation. So that is the Moore's law and the challenge that we have in the VLSI industry. So just to compare, So in 1971, if I'm not wrong, man landed on the moon, and the computer that was guiding that mission was Apollo guidance computer. And the latest Snapdragon chips that we have in our mobile phones today is, let's take for an example, Snapdragon 8 Gen 2. Of course, we have much higher versions than this, but just for the sake of comparison. So if you compare that, a device which was capable of taking the rocket to the moon was running on just a clock speed of 2.048 megahertz. That means for performing one computation, it would take 1 by 2.048 into 10 to the power 6 seconds, right? So it would take around 0.5 microsecond. However, your mobile phone can do it in a matter of nanoseconds. So you see, the computation is also huge. The RAM which was there in the computer was just 4 KB. Now you can support RAMs up to 12 GB is a norm in today's mobile phones. The memory that the device was carrying was 32 KB. Now you can go easily up to 512 GBs. And for reading every word, that means for reading every 16 bits out of this memory, this computer needed 11.72 microseconds, whereas for reading a 64-bit word, the Snapdragon just need 23 nanoseconds. And the dimension of this computer was 60 centimeter cross 30 cross 15 centimeter, and it weighed 30 kg. Now, how heavy is your mobile? Just few hundred grams, right? So what to talk about the processor that is making it, and the cost. As our director sir was saying, that electronics is something which is very affordable. So for making a computer of the capability of Apollo, the cost could have been 1.5 million today, but you can easily buy a Snapdragon for anything less than $150, right? So this is a, a surprising aspect of the VLSI. Even if it is very complicated, it is very affordable to the general public. Now, what is the trade-off in the VLSI? So we play with three numbers: power, performance, area. You can relate it to your mobile phone, right? You want the maximum performance, but you also want the maximum battery life. And you want the mobile phone to be lighter. And when I'm talking from the VLSI point of view, I want the chip to be as small as possible, because every micrometer square that I am giving is $1 for me. The smaller the chip, the more number of chips I can fabricate at a time, and lesser is the cost of the chip. So we always try to reduce these three parameters, and these have been the guiding three variables since the semiconductor design began. So this was pretty much the challenges that we have in the VLSI industry. So these are the challenges which I think, if you come into the VLSI industry, or if you call yourself an electronics engineer, so you should always look up to these two parameters. That is, for every given area of silicon, you should look to double the performance and reduce the power and area as much as possible. So now we will be delving into the design flow of how actually the VLSI industry works. And after this, we will be talking about the opportunities that you as a BTech engineer can pursue or look forward to having in the industry, right? So I have mellowed it down so that the complex flows are understandable for anyone from the first year up till the final year, right? So let's see if we can understand this. So see, it might look scary, but this is the entire flow of a digital chip design. So first I would touch up on what is an ASIC. ASIC stands for application specific integrated circuit. So the design methodology that we are talking about, it is meant for something, or it is meant for an integrated circuits whose application is predetermined. For example, if I want to design a chip which will be controlling the let's say and the opening of an airbag of a car, then I know that a chip should perform in such way, right? So the design begins from that specification itself. What is the chip intended to do? Next, we will see how we can achieve that performance or that the requirement. Then once we know what is to be done and what uh, is to be done physically or per se logically, so architecturally, it would be, for example, in the case of our airbag system, architecture would be like simple as this, that if the car detects a collision, if you see that the car has collided, the system should automatically activate the airbags and they should open, right? So this is the logic behind the chip. How it will work is the functional design and the logic design. This is where the engineers come in, right? This is done in two parts. If the design is a digital design, then it has a specific flow. If it is an analog design, then it has a specific flow. For ease of understanding, we are only considering digital design, right? So for digital design, we translate the idea of the chip into a form of coding, which is HDL, hardware description language. So we write the chip, the intention of chip in HDL. Then we do something called synthesis, which makes digital circuits out of the codes written for the logic. That constitutes the circuit design. Once you have the circuits designed, then you can simulate the design to check if the circuit which we have is working as per the system specification or no. If we are satisfied that the circuit that we have in our hands is working as per the specification, then we go for implementing the circuit physically. That means making the hardware out of that circuit. Now, since we are working with integrated circuits, so it cannot happen that we can make individual components. For example, here we can see we have an OR gate, we have an AND gate, we have a NOT gate. It is not that we will be making individual AND gates, OR gates and NOT gates individually and then clubbing them together. Instead, we have to make the entire chip which will be working just like the circuit which is shown. The way it is done is, the method is called physical design. Again, physical design, if you want to go deeper, it has different parts in it: partitioning, floor plan placement, clock tree, signal routing, timing closures. But these are little advanced stuff which I think will not be possible in this overview. We can of course have a detailed discussions on this in the later stage. So coming back to the flow, so once you have the design which can be actually mapped onto the silicon wafer, then we do the physical verification and sign off. What do we do in physical verification? So whatever we have designed physically, we have to check if that physical design can actually work on silicon or not, right? How do we do it? The foundry or the fabrication facility which actually makes the silicon chips, it gives the designer some guidelines that, okay, you have to design the transistor in say this specification. For example, for the distance between the source and the drain should be, let's say, 5 nanometer. If it is a 5 nanometer technology, right? It is 5 nanometer. If it is less than 5 nanometer, then even if the design is working perfectly fine in simulation, when you actually get the silicon, or the integrated circuit, the design may not work. So for checking all these, we have the physical verification. Once that is done, we go for fabrication and then packaging and testing. So fabrication is the actual hardware manufacturing of silicon chips, and after individual chips are created, they are packaged into packages, and then post silicon testing is done. So this is an overview of the ASIC design flow. We will be looking at some of the aspects of this design flow in a little more depth, right? So as I told, that the design where the digital design starts with something called the logic design, right? And that is done using HDL. HDL is an acronym for hardware description language, and it is simply a description of the logic circuits. For example, if I take a very easy example of a multiplexer. So for the first years, if you don't know what is a multiplexer, so multiplexer is a simple circuit which can choose between two inputs, right? So it works like this, that let's say we have two inputs and we have a control signal. Then based on the value that you have on the control signal, the output can have the value inside input 1 or input 2. So digital design only plays with 0 and 1, right? So for example, let's say input 2 has 1 and or let's say input 2 has 0 and input 1 has 1. Now if you give 0 or 1 on select, let's say if you give 1 under select, then the multiplexer, it is a device, it is made of transistors. It will route the value in the input number 1 to your output. So you will have 0 on your output if you give 1 on the control signal. Consequently, if you give 0 to the select control pin, then the input 1 will be shown at the output. So output will show 1. So you see, based on the input that you are giving to the control signal, the output is varying. What is a 0 and what is a 1? 1 is nothing but a high voltage, per se 5 volt. 0 is nothing but 0 voltage. If your device is running on 5 voltage, then your 1 will be equal to 5 volt. And if you don't apply that 5 volt, that is 0 for it. Now, coming back to the HDL design, if you have to make this particular multiplexer onto a silicon, how will you do it? Now, logically, you know that, okay, I have a device, I have a 4-terminal device wherein two are my two inputs, two terminals are my inputs. One is the control input, and based on what I give to the control input, I will have the either input 1 or input 2 on my output. So that can be written or modeled using HDL. HDL is like, for example, you have C++, right? You write a particular logic using C++ language. So Verilog and HDL are two such hardware description languages. So this particular is a Verilog code. So this code is equivalent to this particular logic. So once you have this code, then your first step of designing the architecture or the requirement is done. Now you have to model this particular line of codes into a logic circuit, right? For that, for that we have something called synthesis. But before you go on to making the physical circuit out of this particular Verilog code, you have to check if this code is working as you wanted it to work or no, right? So for that, we have simulation and verification. What is simulation? Simulation is just providing inputs to your design and checking whether the required output you are getting or no, right? So as I was explaining, for a simple multiplexer, based on the value of selection, the output can either be data 0 or data 1. So if I translate this logic to a truth table is nothing but the functionality of this particular device, right? So if I have select 0, then whatever is in my input A will be going to output. You see, if select is 0, then if the input is, input A is this, B is this, right? So whatever is on my input A, it moves on to my output, right? Similarly, if the selection is 1, then whatever is there on input B, that is, if it is 1, 1, then it will go to 1, right? So it is a very simple design, right? We have just two data lines and one control line and one output line. So we can observe the output line by varying these three signals, and we'll end up with these 8 combination, and we can always monitor it. But when the design becomes big, for example, if you have per se 1000 such gates, right, then manually it is not possible to do it, that you will give it 0 1 0 1. How many times will you give? And for every bit that you have, the number of combination also increases to the power of 2. So for automating these, we have our simulation tools, where you can give the 0 1 0 1 as pulses, and consequently the data can be observed, and based on this simulation you can check whether the output is coming out as expected or no. In a nutshell, simulation is a method by which you provide virtual inputs to your circuit and see if the design is working as intended or no. When I say design, it is a purely logical design, something written in a few lines of codes, right? But this few lines of code cannot be written onto a silicon, right? So for that, you have to transform that HDL, hardware description language, into logic gates. That process is called synthesis. So you have a tool, a synthesis tool, which will take in the logical lines that you have written and make a digital circuit for it, such that whatever input that you had intended, the circuit which is the output of the tool, it will also have the same inputs, and the output of the circuit will behave in the same manner as your HDL code was behaving in simulation, right? So at the end of synthesis, you will have a digital circuit like this. Now, when you have a digital circuit, then each component is in itself a logic gate. For example, this is a logic gate, right? So we know that whenever both the inputs of this logic gate are 1, then the output is 1. And if any one of the inputs or all of the outputs or all of the inputs are 0, then output is 0, right? But this is just the logic. It will, implement this logic by the use of transistors. So this black box in itself is made using transistors, and that transistor is then printed onto, or per se fabricated onto the silicon, right? So that process is called the physical design. So synthesis was the process of converting the Verilog or the hardware description language into a logical circuit. Then physical design is the process of mapping this logical circuit into something which can be actually fabricated onto a silicon. So it will give you something like this. So you see the green uh, uh, the green lines or the green structures are metals, the blue structures are also metals, the red is your insulator or the oxide. Then the P type or the doping that we saw previously for during the working of transistors, that we have two areas of heavily doped transistor of heavily doped silicon areas, that is P plus or N plus regions. They are denoted by, let's say, the black box or the yellow box or the uh, pink box correspondingly. So as engineers, we are very good at understanding how the circuit behaves up till this level. But for actually manufacturing this circuit, we transform this into a fabricable design which can actually be fabricated onto a silicon wafer. And this process in itself is called physical design. At the end of this physical design, we get a file called GDS2. So GDS2 is an acronym for graphic data system, and it is just containing basic crude shapes in it. It is a binary file which will instruct my foundry to make certain aspects during the fabrication. For example, if I take an example of a standard GDS cell, then you see there are multiple layers in which the fabrication is done. So this is my silicon, then this is my oxide, then these are different metal connections. So my GDS file will have the information like this. So I have to make a chip which will have 4 layers. So 1, 2, 3, 4. First layer is of silicon, second layer is of oxide, third layer is of metal, fourth layer is of metal. And then the fourth layer will have metals in this shape, the third layer will have metal in this shape, the second layer will have oxide in this shape, and the doping of the silicon in first layer has to be maintained at a particular concentration, right? So just looking at the GDS, it is not very easy to know what exactly the silicon will be doing, but it is very easy to make a mask out of it. Mask. We'll be discussing this more in the fabrication sector. So the GDS2 file is the output of my design process, which we give to the foundry, which actually makes the ICs out of my silicon wafer. Now, if we go back to the MOSFET, right? So during the introduction, we told that MOSFET is in the semiconductor physical form is nothing but a semiconductor wafer where the body is p-type and two heavily doped n-type regions are there, and then we have an oxide layer of SiO2 grown onto the substrate, and we have metal connections attached to it, right? How will the GDS2 form look like for this particular MOSFET? How will the foundry actually make this? So as we discussed, that the GDS2 file just has crude information on how many layers the foundry has to make, what layers the foundry has to make, and what is the shape of each layer, right? So here, this particular MOSFET is transformed into the fabricable design, and it is having 5 layers. First layer is of SiC, silicon carbide. So I'm instructing the foundry to take a silicon carbide wafer, then deposit graphene onto it, which constitutes my second layer. Then we will have 3 layers of metals, which will be making these connectors, right? So if the foundry is able to give me these layers onto a semiconductor or per se silicon carbide wafer, then if I connect the terminals in my packaged chip, this will come as a packaged chip where it will be source, it will be gate, it will be my drain. Then if I see the behavior of this by applying a potential, as we discussed, like if we apply a potential here and then we apply a high potential here, then current flows between this, right? So if the foundry has made the design like this, then the performance or the working will be exactly what we were discussing when we were discussing MOSFET. So this is how a MOSFET looks when we go into fabrication. And how do we actually transform this information onto silicon? That process is called lithography. See, lithography is a prehistoric term. Litho means stones. We used stamps for making any signature. Like if we go anywhere, then any designation, then any designated officer will sign and then they'll put a stamp on it. That stamp has a pattern engraved on it, and no matter how many times I use that stamp, it will give me the exact same pattern, right? Silicon manufacturing or fabrication is also identical to that. The data that I gave to the foundry as GDS2, geometric data stream 2, is the version of it. It will make a mask out of it. Mask is nothing but it is like a stamp. So when there is a mask and then we have light, in this example it is a UV light, or we can have materials or electrons bombarded on through this mask. Then we have the lens which makes sure that whatever pattern was made on the mask, the same pattern is engraved onto an area of silicon. So if we have the mask for any design, then we can make multiple designs onto a silicon wafer. So this colorful thing is the silicon wafer, and based on the size of individual GDS2 file, you can make n number of silicon ICs or integrated circuits onto it. Then once the entire wafer is full of all the integrated circuits, then we cut individual integrated circuits and then we go for packaging. Of course, before cutting these packages, we test if the design is working properly or no by doing electronic wafer sort, so that we choose the wafer which has the maximum number of working ICs in it. So this is a very crude example of how the design which was given to the foundry in the format of GDS2 is actually manufactured onto a hardware or onto a silicon wafer. So the fabrication process, again, it is something very sophisticated, and it requires a clean room for it. I think clean rooms are fabrication facilities which are having air cleanliness to the levels of 100 particles per cubic meter. For example, in the day-to-day life, we have trillions and trillions of impurities around us. Like there can be dust particles, there can be different oxides floating across the environment, but we cannot afford to have even a single impurity. The reason being, any impurity can be of the order per se, say 10 micrometer, right, or say 10 nanometer, that is 10 to the power of minus 9, 10 to the power of minus 9 meters. It is very small, right? But my transistor itself is just 5 nanometer. So if one impurity is there, then my whole performance of the chip is jeopardized. To prevent that, we have facilities called clean rooms, wherein there are literally no impurities present in the fabrication facility, right? So in the fabrication facility, we have the silicon ingots, which are cut into silicon wafers. The size of the wafers determines how many integrated circuits you can print at a time. Then we have the lithography process. Then we have etching, heating, ion implantation, mechanical polishing. And once we reach to this stage, one layer is done. Like we discussed back in this, that if I have to make, for example, 5 layers, right? Then I have to go through this process 5 times. But for a typical IC, this cycle is repeated 30 to 40 times. Then finally, the wafer fabrication is complete. Then individual ICs are diced and are individually packaged. Right. So this completes the overview of how any logic is transformed into a hardware, or any logic or any idea is designed electronically. Then that electronic circuit is transferred to silicon. Right. Now, let's move to the last section, and I think the most interesting section of the opportunities that the VLSI industry offers to any electronic engineer. Right. So it is not like that every electronic engineer, or per se any VLSI engineer, knows all the steps of the electronic design flow, right? So we have different specializations, and every engineer is specialized in their own field. For example, I am working with static timing analysis, so I will be only dealing with this section of the industry. So based on your interest, you can choose different specializations to pursue in the VLSI. You can go for the HDL design or the RTL design. Then you can go for design for testability, that is inserting some test logics onto the design so that you can check if your chip is working properly or not. For example, if I am designing a chip which is controlling the car's airbag, then I cannot actually check my system, right? I cannot, go and hit my new car and see if the system is working or properly or no. That can only be checked when you actually meet with an accident, unfortunately. But if I am the chip manufacturer, then I have to make sure that the chip is working as intended, right? For that, I will insert some test logics in it, so that if that test logic is working properly, that I can be 100% sure that when the car meets an accident, the airbags will pop up. For that, we have DFT. It is a very new topic, and it is the hot cake in the VLSI industry as of now. Then you can go for physical design, you can go for verification, then you can go for testing, either verification or the device testing. Testing is of two types. One is the verification, where you actually simulate the digital circuits and check if the circuit is actually behaving as the logic was intended or no. The second stage of testing comes when you have the physical silicon with you. When you have the IC, when you have the chip, you put it into a tester and run a test pattern to it and check if it is working properly or no. Then you can also go for specialization in fabrication, but fabrication is very limited in India. Right now, we only have one facility, SCL Semiconductor Laboratory, Chandigarh, and it is a government facility which is capable of making design of 180 nanometer, and now it has started making 19 nanometer as well. But recently it was in news that Vedanta is entering the fabrication business in India. Let's see how it goes. Then again, you can also go for EDA, electronic design automation. Like all the designs that are done in the VLSI industry, they are done through softwares, right? So any person, any CS computer science enthusiast, they can come up with an algorithm to to achieve the designs in the best possible manner in the least possible time. It is done through electronic tools, and even computer science engineers have a very bright future in the VLSI industry. So it is not that only electronics people can enter the VLSI industry. Based on the EDA part, it is totally coding driven. It is, and even the EDA is now inculcating artificial intelligence to it, so that your tool will know what is to be done best based on the previous devices that it had made. For example, if I have to make three ICs, right, and I have already made two ICs, and I see there are some failures, right, then I can give that data to my software, and the tool will automatically take care while designing my third chip, so that the third chip will not have the defects that the first two chips were having. You see, the tool will automatically learn what adjustment it has to make, right? It is totally dependent on software. So even computer science people can also enter it. Now we will just brush up again through the digital design. Now from the perspective of opportunities, we saw that how you can design a specific IC from inception to circuit to physical design to fabrication. How every step has opportunities for you, that is explored in this section. So the design specifications, it is the thing of the dreamers. That's why Steve Jobs is hailed so much. He was a dreamer. He could imagine that there can be a tablet which is between a phone and a laptop, and it will revolutionize the way we use the internet, right? So you can go for that in the design specifications. Then once that is done, if you want to join the HDL part or the hardware description language part, then you can be an RTL designer. RTL is register transfer level. It is the name for the people who design or who write the Verilog codes for the logic defined by the design specifications, and the tools or skills that you need for that are Verilog, System Verilog, HDL. Then once the design is done, and if you want to join the simulation part, then you can look for something called verification engineer. Then you have to learn the skill set of Verilog assertions. Then if you are interested in designing the digital circuits out of the line of codes that your RTL designer wrote, then you can be a synthesis engineer, wherein the tools that you will be using are DC compiler, formality, spyglass. Here, these all are EDA tools. So if you are keen on to joining the EDA business, then you can look for the companies which are making these tools, right? Then if you want to be a STN engineer like me, then you will be working with timing concepts, and you'll be using tools like prime time tempers. And if you want to insert test logic for checking your integrated circuits, then you can be a DFT engineer. Then you'll be using something called Tetramax, a tool called Tetramax. Then again, once the DFT engineers have inserted their test logic, then the ST engineer again has to see if that logic is working as intended or no. Then again, there is a scope for an ST engineer. Once that part is done, then the physical design actually begins, which has different checkpoints for it: floor plan placement, CTS routing, PRO or sign-off checks. These all are done by physical design engineer, and you'll be using tools like Unovus or ICEC. Then again, once the physical design is done, then you need to check if the physical design that you made, if it will work on the foundry or no. For that, you will again be working with the physical verification guys. So you can join this field as well. Or if you want to actually work on the sections or where the design is imprinted on the silicon, or if you want to work in the foundries, then you can join the fabrication. And if you want to work in the testing section where the manufactured ICs are tested, then you can join the testing industry, right? So as you can see, there is a lot of opportunity there in the semiconductor market. And correspondingly, these all companies, to name a few, there are n number of more companies which are operational in India, which are working in the semiconductor field. You can see a lot of coding companies, for example, Google. It has also entered the semiconductor business. Even Facebook has entered now. So, like Google is now making its own chips, right? We had Tensor and all. So you see the opportunities that you have in electronics field are better, if not at least at par with those available in your coding industry. So I hope you will be interested more in the semiconductors as well. So with this, I would like to open the session for questions. So, team, if we can have questions, then we can take up one by one. Okay, let's start.
Thank you, sir. Thank you
The
so
first
much. We have
question.
learned a lot from
I'll
you,
be
sir.
happy with as many questions as you ask.
Actually, we
So,
only get. Yes, sir. Actually, we only get to know the MacBook and M1 chip and NVIDIA, GTX, RTX. But this was the base of all that.
okay. So the first question is from Rajat. As my branch is electrical, what is the roadmap I should follow to enter the semiconductor microprocessor industry? I want to learn VLSI, right?
Sir, this question is from Vineet Kumar.
Okay, so this is from Vineet Kumar. Okay,
Yes, sir.
Yes,
hi
sir.
Vineet. So Vineet, which year are you in?
So first year.
Okay, hi. So, Vineet, if you could see the presentation that we had, there was no bifurcation between electrical and electronics. If I remember the curriculum at our BIT Sindri correctly, then the point of bifurcation between electronics engineering and electrical engineering is basically when electrical people study about electrical machines and electronics and communication people delve deeper into communications, right? So even if you are into electrical engineering, it doesn't mean that it will be difficult for you to enter the industry. So the subjects which are required for entering the electronics engineering are actually taught both in electrical engineering, electronics engineering, and even some topics are taught in computer science and engineering as well. For example, you will be studying digital electronics, which is common for, I think, CS and IT as well. You will be studying analog electronics, which the electronics and electrical people will be studying together. Then you will be studying control systems. That will be again common to electronics and electrical people both. So it doesn't matter if you are in electrical or if you are in electronics, just you have to focus on the subject. What subjects do you have to focus on? Digital electronics, analog electronics, control systems, semiconductors, and anything which will help you to gain a better understanding of the electron flow. To be simple.
Thank you, sir. That answer would really help Vineet. So the next question is, uh, I think it is also in the chat box. How will the semiconductor chip plant that is in making in Gujarat will impact us?
Okay, yes. So as I mentioned, it is being uh, set up by Vedanta, if I'm not wrong. See, India currently is the biggest hub for electronics chips, the design of electronics chips, if you take it in the right way, right? So once we have the fabrication as well, then we will have more opportunities
I
in the fabrication section as well. Am I audible?
Yes, sir, now you're audible.
Hello, am I audible?
actually, guys, yes, sir. Yes. Now you are audible, sir.
Hello.
So actually, there was some glitch.
Yes, sir. You are audible, sir. You are talking about Vedanta. What do you think, Ayushi? If you are given a chance to choose in between IT sector or electronic sector, what will you choose?
Now I think I should go for
Um,
electronics.
I am audible or no?
Yes, sir, you are audible,
Yes,
sir.
sir.
Okay. So to answer him better, I think if I go back to this specialization slide, see, if you will see that right now, as I mentioned, India is already having excellent opportunities in all these sections: RTL design, DFT, STA, EDA is also India is leading, physical design, verification, analog design. Even testing is also substantial in India, but fabrication section of the VLSI industry is not there in India at the stage that we expected. The reason being why it is not there in India as of now, because uh, fabs or the fabrication facilities go outdate very fast. For example, today you are using uh, mobile phones running Qualcomm 888, which are fabricated on, let's say, 5 nanometer, right? Just 3 years back, that fabrication facility would have been
Exactly, sir.
making chips of 180 nanometer, right? So you have to keep on upgrading, and the
Exactly.
cost
We are
involved in it.
the technology has changed.
Yes, yes. So once this fabrication part also
Right,
starts in
sir.
India, then it will increase the opportunities for VLSI. But that being said, that does not mean until the facility is made or until the chip is or the manufacturing facility is available, only then the industry will boom. It is already booming, and even if the fabrication facility is not set up in the timeline, you will have n number of opportunities there. There is no question on that. Of course it will have a positive impact, but that will not be a gating factor for you, at least for uh, people who are aspiring to be in the core design sections.
Okay, sir, thank you so much.
Yeah.
Sir, here is a question. People prefer IT sector for lucrative job offers. Does electronic sector job offers match this one given by IT sector?
Okay, I think this would have been the first question that anyone who is joining or who would have seen the posters would have in their heart. Okay, numbers. What can you expect when you join the IT industry as a fresher? Let me ask you back. What is the average package of IT from BIT Sindri?
So
Sir,
it's
I think
seven
for IT sector, it would be nearly 10 to 12 lakhs, sir.
Okay, and
average.
that is the best thing that I think you are telling. Uh,
Yes, sir.
Sir,
yeah, and
average
what is the
7 lakh.
average that you can, if I want to, if I was in third year of my
Sir,
BTech at BIT Sindri,
So
then what
7
is the
lakh.
best package that I would be looking? You said it can be 10 to 12 lakhs, right?
Yes,
But
sir.
the 10 to 12 lakh people will be just handful, right? Where
Yes,
will
sir.
the, let's say, 60% of the CSIT land? How much package do you expect?
So 5 to 6 lakhs.
7,
Yeah.
7 to 8, right.
Yeah, but that is also a very optimistic number. Let's be realistic, right? But at least if you join the VLSI industry, you will never
Actually,
start
sir, the
with
competition is
zero.
so hard. This is the only
Actually, that is
reason
the
the
point. That
people
is
are
the
doing
point.
moonlighting.
See, the thing, yeah, moonlighting was also very much into the news these days. See, let's talk from the ground reality, right? Any CSIT person who enters into the IT industry, first, the competition is tough. Why is the competition tough? Because even a mechanical guy can read electronics. Oh, sorry, he can learn to code in, let's say, an year, and he can give you a tough competition in during the placements, right? But it might happen that a person who is actually going through the curriculum of CS and IT, he will not have the skills required in the IT industry, right? And he might land up with a average job which will only pay around, say, 3 to 4 lakhs, right? In the electronics industry, you have multiple edges. First, you are a specialist of your field, only then you can enter. The reason why we see very few people joining in the electronics industry is that it is very technically uh, absorbing, to use the right word, right? Mere superficial knowledge of electronics will not help you a lot, right? So for gaining a deeper insight, you would have to go through masters. So if you look at electronics people, electronics engineers who are actually working in the VLSI industry, you will see almost 80% of the people are holding master's degrees, right? So once you do masters in electronics, you actually gain the insights needed for actually working into the VLSI industry. But that doesn't mean that you cannot gain that insight being an BTech engineer. Come on. So once you have the skill set required to enter the electronics industry, your competition will be very small, right? So the first aspect of opportunities, which was because of tough competition in CSIT, that is removed. Now, if I talk about the packages, that depends on where do you land, right? If you land in a
Yes.
service-based company, what is a service-based company? Service-based company is not like the ones in the CS and IT term, right? In CS and IT, like you work for a client, you just troubleshoot issues, right? Service-based company in the electronics industry is entirely different. It is simply that if you are an engineer in a service-based company, you will be working on the chip of some another product-based company. For example, I work for ST, right? So I am an engineer of ST. I work on the chips that ST manufactures or ST designs, right? But we have multiple people working along with us the same things that we are doing, and they are from service based companies. Why? Because at different stages of the design we need different amount of manpower. So during physical design we, let's say, need 10 people to design the chip, but when the physical design is completed we just need 5 people to analyze that design. Now once you join a product company, the product company cannot do this, that he'll pay you only till you are working and they'll not pay you when you are not working, right? So to reduce the cost, what a product based company does, it hires a service based company, hires 5 engineers who will be doing the same thing that the product engineer is doing in the product based company, just for a short duration, like a contractor, right? So when you join a service based company in IT, it is very difficult to switch back to a product based company, right? Because the profiles or the job that you are doing is entirely different. But that is not true for electronics engineering. If you are working, in fact, if you start your career in a service based company, you will have better understanding of designs, and in fact if you will have deeper insights than people who are working in a product based company, because you will be working on multiple vendors. Like if I am working for a semiconductor service based company, I can be working one day for Intel, I can be working another day for Qualcomm, I can be working on the third day for Google, right? So I have wider opportunities. Consequently, so this is the second aspect when you compare the electronics industry with the IT industry. That even if you join a service-based company, in fact, you are learning more than when you join a product-based company. The third is the monetary aspect. So it totally depends on the skill set that you carry. But for any VLSI engineer, once they start working, you can expect anything around 10 lakhs base plus perks and remunerations. And once you have an experience of per se 3 to 5 years, the packages can be easily around 30 LPA per annum. And even one more edge that I have, that I think that the electronics industry has, is the work life culture, right? It is not always just about the money. Like if you are working with a US client, if you are working for a US client in the IT industry, then you have to be online at the point where your client is online, right? But in the electronics industry, you can work at your own schedule, right? If you have to design something, even if you are designing it for, let's say, uh, Intel US, then you can choose to work at your own time and just have meetings at their time, right? So that balance of life you can have better in the electronics industry. So that is why I think electronics should be the number one preference of anyone who actually wants to, contribute to the semiconductor race. I mean, it is a challenging field. Even the CSIT people have a lot of challenges when it comes to developing tools and all. So I think that would pretty much answer the question.
Thank you so much, sir. That was the
Exactly.
last question.
Yeah.
So
Okay,
that
sir.
was the
So
last.
now, so now I request Professor Imtiaz Ahmed sir, Professor in charge IETE Students Forum, to say a few words for the participants and thank Akash sir for sharing his wisdom. Welcome, sir.
Thank you so much.
Very good
Uh,
evening, sir.
First of all, I congratulate Akash for his wonderful uh, insight and enlightenment to the world of semiconductor and especially VLSI design challenges. And I feel the same Akash Vaibhav which I have seen in 2017 when first that Arduino course has been introduced in the IT club.
Yes.
He was the chairman at that time, and he told me that we can uh, design one course for IoT, and it is high in demand in 2017. And you can see the growth of IoT nowadays. So
Yes, sir.
Akash Vaibhav is visionary right from the beginning, and what he achieved in life is a is a torch. He's a torch bearer, and he gives light to all the electronics students who are here, who are witnessing this webinar. And I must say you all that follow your dream, whatever you dream that you should get a job, you should work on that. And that is the beauty of your working your mind, and you should follow that. And
Exactly.
be sure that you will get success, but you need to have patience and a lot of patience for that. You need to work very hard. And I congratulate IIT club members and IIT student members who have contributed, especially Rajat Chaudhary and Rana, who have worked very hard for the success of this program, and all other members who are involved directly and indirectly. So congratulations from my side to IT Club and to Akash Vaibhav for his enlightening speech. Thank you so
Thanks a
much.
lot, sir. Thanks a lot, sir. Sir, can I add something to it?
Yes, please.
So, like, I was invited for giving an insight into the industry, but one thing that I see, which is even more lucrative than the electronics industry, is the electronics research.
Yes.
Like, for sustaining the Moore's law, as I mentioned, that we need to have twice the number of performance in the same silicon die available, right?
Right.
That cannot be done in the industry without proper research.
Right.
So I would be really very happy if students are more inclined towards the research, because
Right.
industry is something which will always pursue pure passion and
Right.
brilliance. And if
Right.
I think if students are more inclined toward what is being done new in the industry, then they will automatically align with the industry, sir.
Right.
No.
Very
Yes,
true.
sir. So this is one thing that I missed. I think I should have added it in my PPT, but actually I thought that it would be very long. So I would really encourage the viewers that please try to do something, try to at least learn what is new in the industry. For example, previously we had planar MOSFETs. Now we have FinFET. People are
Right.
talking about carbon nanotubes. These are very hot terms. So even if we just Google it out, we'll have so much insight on how things actually work, sir. So I think these will help the students a lot, sir. If we, even if we discuss things in, per se, in third year or final year, then they'll have more interest into electronics, sir.
Right. Very true.
Okay, sir. Thank you so much for enlightening words. Here's thank you so much, sir. Imtiaz Ahmed, sir, our professor in charge, who's constantly been helping us throughout the journey of IET. Thank you so much, sir.
Thanks a lot.
Thank you so much, sir, for such appreciations.
Right.
So, as we have come to the end of the webinar, we would like to present Akash sir with a small token of appreciation and a memento on behalf of IET.
We extend our heartfelt thanks to Sir for sparing us his valuable time and sharing his experience with our viewers. Thank you so much, sir.
Thanks a lot.
Thanks a lot. Thanks a lot.
You can contact sir via LinkedIn.
Yes, yes. I
Now,
think I should. Okay. Yeah.
yes, sir. Now we will be moving forward for our quiz round, sir.
Okay. Okay.
There
Perfect.
is a there is a small Menti quiz round for all the participants and all the viewers of our this video. So have a wait for more
Welcome,
for open
everyone.
that portal.
Welcome, everyone, to this
You
quiz section, the most
you can
interesting
scan this
section.
QR code. Exactly. You can scan this QR code or go to that www.menti.com.
By entering the code 17571829.
Actually,
So make
Ayushi,
this quiz.
we also must have to participate to win those prizes.
Yes, I'm very much excited for this quiz segment. I guess this is the most interesting part.
The pressure we bear is another thing, but the swags or goodies we get is just amazing.
Yes.
So have a wait for more participants to join. Uh, are you guys excited? Have a fire in the chat box, please. I can see the chat box. Are you guys excited?
We do have prize for the winner, a very special prize. So
Must
your
share the links
excitement,
with your
guys.
batchmates. जल्दी जल्दी शेयर करो इस लिंक को. अगर तुम्हारे रूमीज को मिल जाता है तो फिर तुम लोग शेयर कर लेना आपस में प्राइजेस.
That's quite interesting. So what do you think? Shall we start?
Okay. So shall we start, guys? If you are ready, then have a thumbs up in the chat box, guys. I can see the chat box. Have a thumbs up.
Show your excitement, guys.
So, okay. So we are starting the quiz section.
Here comes the first question on the screen. Okay.
Guys, be ready for the first question.
What is the result of ionization in p-n junction on either side of potential barrier? Only 10 seconds left.
The easy question. Don't you
Yes,
think,
it's easy.
Ayushi?
Yes, 3 seconds. 1 second and time's up. Let's see. We have got the maximum correct answer. That's depletion reason. Option C. Expecting the right answer from maximum people. Okay, so here is the leaderboard. Prince Mukhopadhyay with maximum number of points, 916 point. Congratulations, Prince. Followed by Ankit IT and 10 others.
Congratulations, Prince. You are on the top of the leaderboard. Maintain this throughout the session, or there can be a table turn. So, moving on to the next question. Are you ready, guys? Moving on to the next question.
Still participants can join.
Yes, in between also you can turn the table. So the question is, Avalanche diode occurs at, the options are as below. Hurry up, guys, hurry up. It's only 5 seconds left. Hurry up, 3, 2, 1, and time's up.
Okay.
And the correct option was breakdown voltage. Okay, we have got 4 correct options. So let's see, move on to the leaderboard. Let's see who is on the top of the leaderboard. So here we see Ted on the top of the leaderboard with 1541 points, and followed by Prince Mukhopadhyay and the other 10 competitors.
It's very
Congratulations, Ted.
exciting.
Prince, what are you doing? So, moving on to the next question.
Okay. So you guys are excited.
Yes, they are excited, Ayushi.
Yes, that I can see. So here is the question. The output voltage signal of a bridge rectifier is half wave, full wave, bridge rectified signal, or sine wave? Answer fast. We don't have much time.
This is the
And then
hard one.
time's up. Okay, we have got correct answer, but still, full wave rectifier. Full wave is the correct answer. Okay, let's move to the leaderboard. काफी सही जा रहा है ये लोग. Sonu on the top with 1716 points.
Okay, followed by Ted and Rahul Kumar, and then Prince Mukhopadhyay and the other 10. So, Sonu,
Okay.
congratulations with 1716 points. So, moving to the next question, the fourth question.
I think the winner will be very unpredictable. With every question,
Yes, we have got the top on the leaderboard chain. The question is, Zener diode can be described as? Okay, so the question number 4 is, Zener diode can be described as, let's see the options.
Hurry
हम
up,
नहीं पढ़ने
guys.
जा रहे हैं इतना सारा ऑप्शन.
Let them read, let them answer. They are getting the prizes.
Time's up, guys. We have got four correct options, and the B was the correct option, a device with constant voltage. So moving to the leaderboard, let's see the unpredictable leaderboard. Who is the new champion, or who is the new top on the leaderboard? Again, I
Okay.
think we have got the next leader. Next,
Rahul Kumar,
Rahul Kumar is on the top of the leaderboard with 1911 points.
followed by Sonu with 1716 points, and then Tate with 1541
And then
points.
Brown Kudi, and then Vroom, and then
What
Prince
do you think
Mukhopadhyay.
about the winner?
I think it would be unpredictable. The four questions
Yes.
and the four leaderboard
The,
toppers.
yeah. Yes. So I guess
So, are you guys excited for the table turn question?
and to see the winner. So
So, this will be the deciding factor.
okay, number of PN junction in a transistor. It's very easy.
We
Hurry
have
up,
read in
guys. Answer this question very
12th
wisely.
class. This will be the
Three,
deciding factor.
2, 1, and time's up. Let's
And
see.
the
Wow.
new topper, and the new topper, or the
Wait before going to the leaderboard.
okay.
Okay. Let's see the winner. Rahul Kumar is the winner with
So Rahul Kumar,
2,727
you are the
points.
winner. Congratulations. Congratulations, Rahul. Please mention
Congratulations,
your
Rahul.
branch and roll number in the comment section. Rahul, please mention your branch and roll number in the comment section so we can contact you for the further processes.
For the
Congratulations, Rahul.
prize.
Must share. अगर तुम्हारे रूमीज तुम्हें हेल्प किए हैं तो उनके साथ शेयर जरूर करना. So, next, before leaving, do fill the feedback form. The link is in the comment section. If anyone has any doubts, then they can contact us on our social media handles also. But wait. Do you know what books to follow and where to get them? And are there any resources to help me scoring well in the upcoming examinations? Where to get the past year's question paper? These are the recurring queries in every fresher's mind. So now you need not worry any longer. We have IETE Students Forum. So Ayushi, can you give a brief about that?
Yes, of
How
course.
can they get those?
Yes, of course. IETE Students Forum has just the thing to help you with your academics. Visit blog.ietbits.com, click on academics, and you will have access to the links to all the books that you need, the past year's question papers, and many more. Do visit
Also,
IET
we
Wishes.
have a blog. Also, we have a blogging section where you can give your personal blog, which can be updated on the IET's website, or you can read those blogs. So, IET wishes you all the best for your BTech journey. Happy reading. And lastly, we want to thank our viewers for connecting with us and making this a massive success. Thank you and best of luck to everyone. So, guys, be ready for the next webinar, which is going to be held tomorrow.
That will be also quite interesting. We'll get to know different things. As it's your first year, you will be exploring
Are
things.
you guys ready for the next webinar, which is going to be held tomorrow? Acha, can you guess the topic? Okay. Okay.
Thank you so much, everyone.
Thank you, guys. So be ready for the next webinar. We will meet tomorrow at 6 p.m. and we will again have such an interacting session with you all.
You will get to know many more new things. You will learn. You will grow.